our next presenter is Mai Ando, who's in our SciTech group. He'll be talking about efficiency and resource evaluation of in situ workflows. Welcome to.
Okay, so hello everyone. So my name is Situ. I'm a 4th PhD student in computer science at the University of Southern California, and I'm also a graduate assistant in the SciTech group at SI. So my research covers several areas in data analytics and high performance computing. And today I'm going to present one of my research topics, that is efficiency and resource evaluation of in situ workflows. So for the analyze, so first I will go over some motivation and several background knowledge as well as the problems. And after I state the problems, I will come to the approach and some result that I got. And at the end, it will be the conclusion in the future work. Okay, so for the motivation and background, so basically this work is start from a domain-specific application. So that is the molecular dynamics simulation. So molecular dynamics simulation is one of a very popular simulation nowadays that emulate the atomic interactions of molecular system that evolves over time. And the reason that we study molecular dynamics simulation is to help the scientists to have the better understanding about the molecular system. So because of that, you can see molecular dynamics simulation has been used widely in many fields, as you can see here, like chemistry, material science, molecular biology, or drug design. And the evaluations of many HPC systems nowadays, as well as some MD software related methods that have the MD simulation to achieve the ever increasing scale, which generate a large amount of data, and to be able to analyze these that large amount of data. So the data traditionally the data need to be stored in the file system first, and after that it will be retrieved for processing. However, because the I/O bandwidth that does not grow at the same pace with the computing capabilities of the hardware technologies, so the I/O bandwidth or the I/O limitation will become the I/O bottleneck when we want to save large amount of data on the file system. Okay, so instead of post-processing data, like you have to save large amount of data to the file system. So there is an alternative processing paradigms that has been emerged that we call it in situ processing. So for in situ processing, the data is analyzed as generated by the simulation. So specifically, the data will be generated by the simulation over iteration, and at each iteration, the simulation data will be stayed to the analysis for processing, and in that way, we can process the data on the fly and when the simulation running as well. And in situ processing allows us to reduce the I/O bottleneck and also to overcome the large data footprint that we have on the file system. And on the other hand, the simulation and the analysis task will be interleaved their execution to each other, so we can improve the overall performance as well as reduce the time to the solution of the pipeline of the simulation and the analysis. Okay, and in another perspective, when we have the HPC system, and the HPC system also allow us to run at the same time a series of simulation due to the powerful computing powers. So that is the reason why nowadays recently we have several example-based methods that you can see. I can list a few here. For example, the multi-workers or the generalized example. And this example-based method actually motivate the need to run multiple simulation in examples. And in this work, we revisit the definition of a workflow example, as you can see in the diagram on the right slide. So a workflow example is comprised of multiple example members of workflow that run concurrently to each other. And in each example members, we have the simulation coupled with the analysis using in situ processing. And we call the simulation and the analysis here as the example component. So according to this diagram, so we can classify the workflow example in 3 levels of granularities. The first one is the example components, that is the simulation and the analysis. And the second one is example members of workflow. And the last one is workflow example. Then again, in this work, we focus on the example of in situ workflows. Okay, and using in situ processing, which means that often imply that the simulation and the analysis usually need to place on the same set of resource or the same set of compute nodes, so that the analysis can take the data generated by the simulation locally, and we don't have to move the data across node. So we can reduce the overhead of moving data. But collocations usually lead to the resource contention if we do not manage efficiently the simulation, the coupling of the simulation and the analysis. And in workflow examples, when we have many components that couple to each other, the resource contention can be worsened. So that is the reason why we think in order to evaluate the performance of workflow example, we somehow need to take into account the collocation here. Okay, so at the beginning, we first conduct a very initial experiment to characterize the collocation. We introduce a set of metrics. As you can see in the table, these are the traditional metrics. As you can see, we have the execution times, we have the last level cache miss gradual, memory intensive, to be able to describe the level of contention, instruction per cycle. We can also have some maxband at the level of example member and workflow example as well. Due to the time constraint of this presentation, so I will not show the result that I got from this experiment. But however, I see we see some limitation when using these traditional metrics. Like if we only evaluate these metrics exclusively, so it does not guarantee that we can have the full understanding of the performance of the workflow example, because example component in the workflow example can be coupled data to each other and can be synchronized to each other. So one example component slowdown can lead to another example component slowdown as well. And for example, if we have one example members that run pretty slow compared to the other example, it can become the straggler of the workflow example. So based on this observation, we think that we need to develop a method that can capture the performance of the workflow example at multiple levels of the workflow example. Okay, so that is the motivation of the work. And now we come to the approach and the result. So this work basically based on one of the previous work that we did, that is introduce an in-situ efficiency models, and we apply this in-situ efficiency model at the level of ensemble members. And this in-situ execution model, so we use it to characterize the execution of the ensemble members. And based on these models, we propose one of an indicators to estimate the computational efficiency of the ensemble members. So by saying computational efficiency, we mean that we measure the time during the execution of the ensemble member that the ensemble component do not sit idle, and we take that time to estimate the computational efficiency. So if you would like to have more detail about this work, so you can take a look at the reference that I put at the below of the slide. And we leverage this computational efficiency indicator and extend it to evaluate the performance of the entire workflow example. Okay, so now let's come to the main idea of this work. So since we have the computational efficiency that we proposed in the previous slide, so we leverage it and extend it to introduce a multi-stage approach. By saying multi-stage approach, we mean that at each stage, we will add one more layer of the performance information to the performance indicators so that we can evaluate multiple design resource features. For example, the resource usage, the resource provisioning, and the resource allocation of the workflow example. And at the end, we propose an objective function to aggregate these indicators into a global indicators, as you can see in the diagrams. So for this diagram, based on the execution of each example members, we will compute the computational efficiency. And after that, we extend this computational efficiency to the resource usage. And secondly, we add one more layer of the resource provisioning on top of the resource usage to the performance indicator. And at the last stage, we add the resource allocation into this performance indicator. So finally, we have one performance indicators for the example member one that we call a PI. So similarly with example member two, we also have B2. And for example member three, we also have B3. And these performance indicators will serve as the input for an objective function that will aggregate these indicators into one performance indicators at the level of workflow example. And we would like to maximize this objective function to be able to maximize the efficiency of the workflow example. Okay, so for the experiment, so for the experiment setup, so we conduct the experiment on a workflow example of molecular dynamic use case. So that is the reason why we, for the simulation, we use one of medium scale on atom system. And for the analysis, we use one of specific analysis that we call it collective variables that actually compute the largest eigenvalues of the Piper time matrix. And we also implement one runtime system to be able to couple between the simulation and the analysis using an in-memory staging area. So the data that generated by the simulation will be stayed from memory to memory from the simulation to the analysis. Okay, so for the experiment here and some result that I got, so you can see here, we actually apply the performance indicator that we proposed in the previous slide over several set of configuration. So the configuration will specify the number of compute nodes that apply to the workflow example, the number of example member that has in that workflow example, and how the example component will be mapped into the resource that we allocate here. And you see we for example, in this table, we have two configuration that has one example member and 5 configuration that has 2 example members. And so we focus on the last 5 configuration that have 2 example members. And for the plot, you see these are the plot that demonstrate the objective function over several performance indicators. So basically we should focus on the last plot where we have the performance indicator that already include all the state that we proposed in the previous slide. And you see here, C1.5 is the configuration that result in the best objective, result in the max objective function. So if we map C1.5 into this table, so that is the placement where we place the simulation and the analysis of the same example members on the same set of resource. For example, simulation 1 and simulation and analysis 1 on node 0, and simulation 2 and analysis 2 on node 1. So with the our performance of C1.5 compared to the others configuration, so we confirm that we have the benefit when we want to collocate couple components together. Okay, so now let's come to the conclusion. So in this work, we have proposed several performance indicators to capture the performance workflow example in multiple perspectives: resource usage efficiency, resource allocation, resource provisioning, and we apply these proposed indicators in the molecular dynamic use case, and we show that we have some advantage of data locality when we co-locating couple components together. And for the future work, we will use this method in the problem of scheduling, that we would like to schedule the institute component under the resource constraint. Okay, so that's pretty much what I want to say. So if you have a question, so I'm happy to take all of your questions.
Thank you, Tu. We have time for one question. So if somebody has a question for Tu, speak up, because I cannot see everybody. And if not, I have a question to, how easy would it be? So you talked about the molecular dynamics application as a motivator for this work. How easy would it be to adapt these methods to a different type of application?
So different type application. So what are the different type applications?
Another type of in situ application from another domain.
Yeah. So basically, for the framework that framework that I showed you here. So basically, the framework here have abstract the data that generate by the simulation here. So it means that the data that generate by the simulation here can be generalized to the other simulation as well. So actually, this framework is not only focused on molecular dynamics with the data abstraction. So for the data abstraction here, I think we can apply it to the other type of simulation and also the other type of data that generated by the other application as well.